Okay. One coin toss. Head or tails? Okay, we are going to count a heads as a value of 1 and a tails as a value of 0. Okay, so head is our success, essentially, right? So head value of 1, tail is a failure, so value of 0. Okay, so if I flip the coin one time, then I can get either a heads, which means that the value of x would be 1, or I can get a tails, which means that the value of x is 0, right? Now, if I draw a probability distribution for this, then I get simply this. Sorry, it should be 0, 1. I'm not backwards enough already. And that's it, right? Two coin tosses. What are the possible outcomes?
Heads,
Heads, heads.
Heads, tails.
Heads, tails.
Tails,
Tails, heads. And tails, tails. Okay, what's the probability for each of those? 1/4. 1/4. 1/4. 1/4. Now, if x, our random variable, is the number of heads, then what is the value of x here? The value of x is 2. The value of x here is 1. The value of x here is 1. The value of x here is 0. Okay? Now, there's 4 possible outcomes, right? So, if I were to take each of these, so the probability of getting a 2 is 1/4. The probability of getting 1 is 1/2. And the probability of 0 is 1/4, correct? All right. So if I get 1 head on the first coin and 1 head on the second coin, what is the average number of heads I get on each coin flip? 1, right? Because each time, on average, if I were to get this, the average number of heads is 1. Okay, so x bar for the first situation is 1, and there is a 1/4 probability that that's going to happen. Okay? What is the average number of heads for these two? 0.5. Okay, so the average number of heads is 1/2. And the probability of that halving is 1/2. Okay? What is the average number of heads here? 0. All right? Now, if I graph that versus its probability, I now have zeros of 0, 1/2, and 1. The 0 has a probability of 1/4. The 1/2 has a probability of 1/2. And the 1 has a probability of 1/2. Now remember, what this is representing is the average number of heads on each toss. Okay? In other words, that's the sample mean, right? It's the mean for the sample. For each instance, on average, how many heads do I get? And this is our distribution. Okay, everybody with me so far? How about 3 coin tosses? What are the possible outcomes? I can have heads, heads, heads. What else?
Heads, tails, heads, tails, heads, tails, heads, tails, tail, 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 heads, tail, 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 heads, tail, tail, tail.
Got it?
H, T, H, H, T. T, H, H.
We okay now? 2 times 2 times 2 is 8. We got 8 possibilities. Okay, awesome. The value of x here is
3.
3. I got 3 heads. The value of x here is 2, 1, 1, 1, 0,
And 2, 2.
2, 2. Okay, again, let's look at the mean number of heads. What is the mean number of heads here? Out of 3 trials, I got 3 heads, so on average,
1.
1. Average,
2.
on average,
1.
on average. Okay, same thing all the way down, right? Believe it or not, this does have a point. Okay, so the average number of heads. Now, let's put down our probabilities. We have 8 different situations. Out of how many do I get 0?
1.
1 over 8. Okay, how many do I get 1/3? 3 over. So 3 times as tall. Okay. 2/3.
3 times. 3 over 8.
Great.
1.
And then an average of 1 is back to 1 over 8. Okay. What?
Looks like a normal distribution.
It does look like a normal distribution. Okay, this will lead us eventually to what is called the central limit theorem. Okay, the central limit theorem says this, and we're not going to go any further because it's just going to get even more annoying after that. The central limit theorem says that as n gets big, or large, as n gets large, so n is the number of trials, the sample mean approaches a normal distribution.
So technically, all the probability functions that we learned, if the n value increases, they all look like normal distribution functions, except some exceptions, such as probability, burden.
That's not what this is saying. What this is saying is that the sample mean distribution
Also
will be a normal distribution, not the distribution of the data, right? This is a binomial, the data itself is a binomial distribution. What we're looking at here is the means, right? Because when you get a mean, you expect to get that number every single time. Some of the time you'll get a little bit to the left, some of the time you'll get a little bit to the right, right? Sometimes you get way to the left and sometimes you'll get way to the right of that average. Therefore, the average number of several trials will give you a normal distribution. If I take this average and that average and that average, those averages will come out to a standard distribution. The data itself, for example, if my n, usually we use 30 for a rule of thumb. N needs to be greater than 30. So if I have 30 data points, those data points themselves will still be a binomial distribution or a Poisson distribution or whatever distribution we've talked about before, geometric, negative binomial. Those individual points, x, that random variable will still have that distribution. But if I average them all together, then I expect them to have this value with a normal distribution. Now what this is going to do is that now if I take a bunch of data and I get the average of that data, then I can now say I can be 68% confident that my average is within one standard deviation of the real average, right? I am 95% certain that the average that I came up with is within 2 standard deviations of the real average, okay? So this is important that when we talk about this, it is this sample mean that is going to create a normal distribution, right? Okay, question.